first talk of our morning session is by Matthieu Astorg from Université d'Orléans, and he will talk about higher order bifurcations in families of skew products.
Thank you. So I would like to start by thanking the organizers for giving me the opportunity to give this talk. And let me also start by apologizing in advance, because this is not going to be a talk about transcendental dynamics. But I still hope that you will find it interesting. So this is a joint work with Fabrizio Bianchi. Okay, so let me start with like the sort of broad picture question motivating the result that I will be presenting in this talk. And the big picture is this. So suppose that you have a holomorphic family of holomorphic dynamical systems. So we'll say which kind of dynamical systems, but for now I'm being very vague. You can think, for example, of the case of rational maps, TBA, on the Riemann sphere. And then there will be a notion of bifurcation locus. Again, I will recall exactly what this means. And then the question that we are sort of interested in this talk will be, is there going to be, is the bifurcation locus going to be homogeneous in some sense? Or are there going to be some special subsets of the bifurcation locus in which something special is going on that is not occurring everywhere in the bifurcation locus? So the question is it going to be, is the bifurcation locus going to be homogeneous, or are there going to be some dynamically special closed subsets of the bifurcation locus in which some stronger kind of bifurcations are going to happen? And in dimension one, we'll recall the existing theory, and we'll see that the answer is yes. We'll explain that how there is a filtration, so a finite decreasing sequence of closed subsets of the bifurcation locus. And the smaller these sets are, and the stronger the bifurcation is in those sets, in some sense. So you have BIF1, that's all of the bifurcation locus, and then BIF2 is going to be some strictly smaller closed subset inside the bifurcation locus, and then you would have an even smaller subset, and it goes on until a bifurcation locus of maximal order. And so this is the picture in dimension one. Dimension one, dynamical dimension one. So let's say for rational maps on the Riemann sphere or polynomials. And we'll see that in higher dimension, the picture is not the same as can be expected. Okay, so let's start by recalling some famous results from dimension one. So this is a theory that was developed in the 80s independently by Matthieu Astorg and Lyubich. So suppose that you have a holomorphic family of rational maps on the Riemann sphere. Then you can define, if you follow holomorphically a critical point with respect to the parameter, so let's call that critical point C lambda, you can say that it is passive over some domain U in the parameter space if the sequence of maps which to a parameter lambda associates the nth iterate f lambda n applied to C of lambda. If this sequence of maps is a normal family, then we say that this critical point is passive, and if not, we say that it is active. So this concept was already introduced in Anne's talk yesterday. And a second notion that will come back again and again during this talk is the notion of a Misiurewicz relation. So when you have a critical point that is preperiodic to a repelling periodic point, we'll call this a Misiurewicz relation. And So that's a Misiurewicz relation. It can be, depending on your family, this could be persistent on all of the family or not. And if it's not persistent, then we'll say that the corresponding parameter is a Misiurewicz parameter. And this is, of course, strongly related to bifurcations. So now let me recall the theorem of Matthieu and Sullivan and Lyubich, which I'm sure most of you know very well. So if you have a simply connected domain in parameter space, then the following are equivalent. So first, all critical points are passive on the domain. Second is that you don't have any, well, you don't have any Misiurewicz parameter, I guess, with the definition. So you don't have any non-persistent Misiurewicz relation. The third property is that you don't have any non-persistent neutral cycles. And the fourth property is that the Julia set moves holomorphically over the domain. You could list other equivalent properties, but these are the ones that I'm going to use in this talk. Okay, is there a question in the chat?
Yeah. Just a short one. Is this several dimension or one complex dimension, this parameter space now?
No. The parameter space.
Yeah.
No, the parameter space here, I think, could be any dimension.
Any dimension, okay, yes, it's okay, good. Yeah.
But this is, for now, this is in dynamical dimension 1. I will talk about I will talk about every possible case in a moment. Okay, so whenever these properties are satisfied, you're in the stability locus, and the complement of the stability locus is defined as a bifurcation locus. Now, there is another way to approach bifurcations in rational dynamics in dimension 1, and it's through potential theory. So recall that there is, if you have a rational map in dimension 1, there is a unique measure called the equilibrium measure that is supported on the Julia set, and that has the property that it's the unique measure that maximizes the entropy. So it's a special measure, and you can look at the quantity that is the average against this measure of log f prime, and this is called a Lyapunov exponent, and it tells you on average how expanding your map is on the Julia set with respect to this measure. And there's a theorem due to Laura de Marco that states that this function, which to a parameter lambda associates the Lyapunov exponent for this measure of maximal entropy, this is a function that is continuous and Curie subharmonic, PSH. Now, what does Curie subharmonic mean? Well, Phil and Gwyneth, Phil, I guess, introduced subharmonic functions in this mini course, and a PSH function is the right generalization to several complex variables of a subharmonic function. So a function L would be, so you should think that L is defined on the parameter space. So it's defined in something that a priori has dimension more than 1. And saying that a function is PSH is saying that it is upper semi-continuous, and that if you restrict to any one-dimensional slice, you get a subharmonic function. So if you restrict to any complex line or complex curve, you should get a subharmonic function. So what does that tell us for bifurcations? Well, second theorem due to Laura de Marco says that the bifurcation locus is exactly the support of the Laplacian of this Lyapunov exponent. So there's a very strong connection between this Lyapunov exponent and bifurcations. And let me say, so first, let me say that this DDC, it really means Laplacian. It's a notation for Laplacian. And let me explain a bit what I mean by this Laplacian. So I think Phil mentioned that when you have a subharmonic function, if you take the Laplacian of a subharmonic function, you get a finite measure. Probably you get a measure. So if you have a parameter space of dimension 1, then the Laplacian of this Lyapunov exponent is a finite measure called a bifurcation measure. And the simplest instance of this is if you look at the space of quadratic polynomials, z squared plus lambda, then this measure, so it's a measure that is supported on the bifurcation locus. So the bifurcation locus is the boundary of the Mandelbrot set, if you're in the quadratic case. And it turns out that this measure is exactly the harmonic measure on the Mandelbrot set. But if in general, if you have a parameter space of higher dimension, then the Laplacian, so you have two derivatives of order 2, and so when you take derivatives of order 2 of a function, what you get is a 2 form. And except that the Lyapunov exponent is not a smooth function with a parameter, it's only continuous. So this is a derivative in the sense of distribution, and so what you get is a 2 form, except that its coefficients, instead of being smooth functions, are in fact distributions, in fact measures. So this type of object is called a current. And I'm not going to talk too much about this, but I just wanted to sort of give the definition. Okay, so when you have a 2 form, what you want to do, one of the basic operations that you can do with differential forms is you can take wedge products. So you can look at this 2 form, DDCL, and take wedge product with each other. Now, it's not obvious that this is actually well defined because there is some analytical subtleties because these are not smooth objects. You have distribution as coefficients, and so the multiplication of these things is not it's not obvious how to define it, but so there are some technical difficulties to be overcome, but it turns out that whenever L is PSH and locally bounded, this you can define this. There's a way to make sense of this object. And here, L is much better than just locally bounded. It's in fact continuous. So, this thing can be defined properly. So you have these. So here, maybe this is not completely clear, but here you have you take the wedge product m times, and you get this object, t bif to the m. And you can take m to be any integer between 1 and the dimension of the parameter space. And when you take m to be exactly the dimension of the parameter space, so what you get is, in some sense, it's a volume form. I mean, it would be a volume form if it was smooth. So in other words, this is a measure. So if you take m to be the maximal integer that you can, what you get is again a finite measure, and these objects are how we define this filtration of bifurcation. So we define the bifurcation set of order m as the support of this object. So for now, it's a really abstract definition, but we will see what this means dynamically. Okay, so the question is, what does it tell us dynamically? So those are, for now, it's a bit of abstract nonsense maybe. We have defined these objects, and what does it tell us from a dynamical point of view. So you can construct these objects for any PSH locally bounded function, but of course here L is a dynamically defined function, and so these objects should tell us something dynamically. Well, the answer is given by, so this is a sort of fusion of the work of many people. So assume that we're looking at the family of rational maps, all rational maps of degree D, up to Möbius conjugacy. And so the first statement is that the bifurcation locus of order M, as defined above, is precisely the locus, the closure of the set of parameters which have M neutral cycles, at least M neutral cycles. And the second statement is that this locus is also exactly the closure in parameter space of the set of parameters where you have M Misiurewicz relations. So M different critical points that are each mapped after some amount of iterations to repelling cycles. Okay, so the first observation is that this is then indeed a strict filtration. So you never have equality between these bifurcation loci, because if you are in the bifurcation locus of order M, then you need to have M critical points that are active. So this is sort of easy to see that if you are in the depth M, in the bifurcation locus of order M, then you need to have at least M critical points that are active. And it turns out that this is actually not sufficient. So I will talk about this in a minute. So, for example, if you look at, let's say, cubic polynomials, you can take, so you have two critical points. Let's call them C1 and C2. And if you take a cubic polynomial where C1 is fixed, and C2, so I think this is possible, right? C2 is Misiurewicz. Then this would be in BIF1, but not in BIF2. So I don't even have I don't have an explicit formula for such a cubic polynomial, but it's probably not too difficult to find explicitly something like this. Now, it turns out that things are a bit more subtle if you want to understand exactly what is in BIF1 but not in BIF2. So here's another more subtle example, which I think is due to Douadi. So I think it's, if you take this polynomial, this cubic polynomial, so what happens is that you have a parabolic fixed point, 0, and you have the two critical points are both captured by the fixed point 0. And so both critical points are active. But, so for example, by Montel, it's very easy to see that you can make a first perturbation so that C1 becomes Misiurewicz. And you can make a second perturbation such that C2 also becomes Misiurewicz. But what you cannot do is make it happen for both at the same time. Because it turns out that this polynomial is what is called parabolic attracting. I think this is the right one. So if you perturb it, the parabolic fixed point at 0 will split into two different fixed points, but one of them is always going to be attracting. And so there's no way that you can, by a small perturbation, make it so that both critical points are Misiurewicz at the same time. It can happen for either, but not for both at the same time. So even for cubic polynomials, it's actually not understood which parameters are in. I mean, so we know some parameters that are in Bif2 and some that are not in Bif2, but the general question of completely describing all parameters that are in Bif2 is actually this is not understood for cubic polynomials. Okay, so this is the picture for bifurcations of higher order in dimension 1, and now let me talk about bifurcations in several complex variables. So in several complex variables, there are many classes of maps that you can study. Anna Miriam talked about transcendental N maps in dimension 2. But in this talk, I'm not going to talk about N maps. I'm going to talk about submaps of PK. So this class will be a good analog in higher dimension of rational maps or polynomial maps in dimension 1. And in fact, we're even going to talk only about polynomial maps and PK. So polynomial map on PK will be just a polynomial map on CK. So you have F1 to Fk, polynomial components. And the condition that allows us to extend this map holomorphically to PK and not just to CK is this condition that for all z large enough, so z is a vector in CK, the norm of f of z should be larger than a constant times the norm of z to the t. So this is exactly the condition that guarantees that your map will extend nicely at infinity. So there are a couple of features that I want to emphasize before stating anything about bifurcations. Things that are different going from a higher dimension than from dimension 1. So the first thing is you have many more critical points. This is sort of the complete opposite of the talk of Anna Miriam, where N maps are automorphisms, so they don't have any critical points, but these maps have many critical points because critical points are given by the equation Jacobian is equal to 0, which is now it's a complex hypersurface. So instead of having finitely many critical points, now you have a whole complex hypersurface of critical points. So that's very different from, let's say, polynomial dynamics in dimension 1, but maybe not so exotic for transcendental dynamics, where you can also have many critical points, of course. And the second property is that there are now different notions of Julia set. So in dimension 1, the Julia set satisfies several properties, but now in higher dimension, you will get different Julia sets satisfying these properties. So you can define a green function as for one-dimensional polynomial maps, and Fornes and Sibony proved that this green function is continuous, and again, it is PSH. And again, as for the bifurcation locus, you can define the Julia set of order M as the support of the Laplacian of G, and then you take M wedge products with itself. And the properties, the meaning of this Julia set is if you look at the largest Julia set, J1, you can prove that it's the complement of the Fatou set, so it's a non-normality locus. And the small Julia set, so the smallest Julia set, Jk, that's going to be the support of the equilibrium measure. The equilibrium measure will be the unique measure of maximal entropy, and it's the measure that is associated to G. And so you again have this sort of same filtration. going on. And here's a very simple example that shows you that you should really not think that J1 and J2 are the same thing, even for nice maps. So if you just take the simplest map that you could think of, f of zw goes to z squared and w squared, then J1, so the non-normality locus, is the union of S1 cross C and C cross S1. But the small Joule set, which is the support of the measure of maximal entropy, and here it's also the closure of the repelling cycles, it's S1 cross S1. So even for the simplest possible maps, like this stratification of Joule set is strict. Okay, so now let's talk about bifurcation in area dimension. So first, the ergodic theory, theoretic part works the same as in dimension 1. So the sum of the Lyapunov exponents. So this time it's the integral of log of the Jacobian. This is again continuous on PSH. And now there's a theorem by Berthelot, Bianchi, and Dupont, which is the basis for the whole theory. And this theorem states that you have the following equivalent properties. So it's equivalent to say that the Laplacian of the sum of the Lyapunov exponents is 0 on the domain U. And it's equivalent to say that almost all of the Joule set moves holomorphically. So it's not as precise as in dimension 1, where you have all of the Joule set that moves holomorphically, but the lambda lemma is not available in every dimension. And so this is why you have this slightly weaker property of the Joule set. And the third property is that you don't have any Misiurewicz parameter in your domain U in parameter space. And whenever, so again, there are more properties equivalent to this, but these are the ones that I'm going to mention in this talk. And whenever this happens, you're in the stability locus, and otherwise you're in the bifurcation locus. And here, so here a Misiurewicz relation means that you have one critical point, at least one critical point that is preperiodic to a repelling cycle. And that repelling cycle is should be in JK, and this should be non-persistent on your family M. And let me also mention, so a new feature of this bifurcation loci in area dimension is that the interior is not empty. So you have what's called robust bifurcations, and that is at the moment this is not this raises many very interesting and challenging questions, and this is not well, there are many things that are not yet understood about this. Okay, so since the sum of the Lyapunov exponent is again continuous and PSH, you could define exactly the same stratification as in dimension 1. So you can look again at the support of these objects, DDCL and M times, and then you can ask what would the dynamical interpretation of these sets be. So before I state our result, let me say that we're not going to work, our result will not apply in the family of all endomorphisms, but it will work with the polynomial skew products. So skew products are maps of this form. So they preserve a foliation by vertical lines, z equals constant, and their components are polynomials of the same degree. So there's this condition on the form of Q that allow you to extend it to P2. And the advantage of working with the screw products is that it's close enough to dimension 1 that some tools remain available. So it's easier to work with them than to work with general endomorphisms of P2. But at the same time, their dynamics is rich enough that you have new things that do not happen in the one-dimensional polynomial dynamics. So, the first examples of wandering domains from polynomial maps were constructed with screw products, and also these results, some of the results about robust bifurcations that I mentioned, even though the statement is in the family of endomorphism, the proof starts from screw products. Okay, so now we can state our result. So we are going to consider the family of all polynomial screw products of a given degree over a fixed base polynomial P. So we fix P, and our parameter space is the set of all polynomials Q that you can take of the same degree. And the theorem is that if you assume that P is not a power map, not a Chebyshev polynomial, and that its true set is not totally disconnected, then all of these bifurcation loci are exactly the same. And another result that we proved that we'll actually get from the proof of the first theorem is that if you take any parameter in the bifurcation locus, then as close to that parameter as you want, you can find a certain hypersurface, local hypersurface in parameter space with non-empty. When you look at the bifurcation locus of just this hypersurface, you get non-empty interior. So that gives many examples of families where you have robust bifurcations. Okay, so now let's in the remaining time, I will try to give some ideas of the proof. Suppose that you have a map lambda naught, so a screw product f lambda naught with a Misiurewicz relation. You can look at the set in parameter space. Well, this relation is preserved. So this will give you a local hypersurface in parameter space, and we'll call that surface hypersurface, let's say M1, the first Misiurewicz relation. So you're looking at the set of parameters where this critical point remain pre-periodic with the same combinatorics to a cycle of the same length, same period, N1. It's an analytic equation, and so that gives you locally at least a hypersurface in parameter space. So the first fact that we are going to use is a sufficient condition to be in BIF M, the bifurcation locus under M, in terms of Misiurewicz relations. So we proved that if you have a map f lambda that has M Misiurewicz relations, and if the locus, well, the loci, well, these Misiurewicz relations intersect each other geometrically in parameter space. So that means that the codimension of the intersection has the codimension that you would expect. Then that parameter must be in the bifurcation locus of order M. So this in dimension 1, this was proved by Adam Epstein and Xavier Buff. And in dimension 1, you don't need this condition on the codimension, because by work of Adam, you get something even better than this for free. But So let me just draw a picture. In higher dimension, it's enough to have a picture like this. So if you have M1 and M2, two loci where the corresponding to two different bifurcation Misiurewicz relations. So M1 and M2 are sets in parameter space where you have two separate Misiurewicz relations that are satisfied. So here you have a parameter lambda that is in the intersection of both. Even if you have a tangency between them, this parameter lambda must be in the BIF2. But in fact, in dimension 1, Adam proved that this cannot happen, that the picture is always more like this. That there's always going to be a transverse intersection between these sets. But this is a priori, this uses tools that are not available in higher dimension. And so
Matthieu, when you say codimension in the general statement for higher dimensions, is that codimension really then in the tangent space or the cotangent space? Because otherwise I don't see.
It's in the parameter space.
So where would the transversality condition come in that phrasing?
Are you talking
or
about
maybe you said in dimension 1, what you don't have to say what, that the codimension.
So I'm saying that if you're looking at, let's say, the modular space of Rational maps of degree D,
yeah,
and you're looking at if you look at some combinatorics of some Misiurewicz combinatorics, maybe you mark all the critical points. Then if you look at the loci where several such critical relations happen, these things intersect each other transversely.
right. I know, but I mean, but you're not just copying that hypothesis into the proposition here. You're replacing it with the statement about intersections. So should I really think of those being intersections of the tangent? It doesn't matter. I thought you had a quick answer. That's all.
No, I just mean we don't need them to be to have transverse intersection. We just need them to have intersection of the right codimension. So it's okay to have tangencies. It's okay to have.
Okay, so in other words, the picture that you drew on the left, if you had that in one dimension, that's also your proposition applies to that also. It says that even that's okay.
Yes,
we didn't
exactly.
need transversality
Exactly.
there. Okay, good.
Okay.
It shows that transversality is irrelevant here.
Well, I mean, it would make things easier, but it's just not there. So
easier and less generality.
Well. And okay, so the second key proposition is that if you have a family M with some assumption that I'm going to mention a bit more precisely in a moment, if you have a family M of skew products, so not necessarily the whole family, and if you have on that family M a Misiurewicz relation that is persistent and that it satisfies also, so that's why I put good, because we also need other properties, but I'll come back to that in a moment. Then in that family, near any parameter in that family, we can find a new non-persistent Misiurewicz relation. And so in particular, in this family, you have robust bifurcations because near any parameter, you can find non-persistent new Misiurewicz relation. So everything is in the bifurcation locus for this family. And this of course, will give you for free the second theorem that I mentioned in the previous slide. And once you have proposition 1 and 2, the idea of the proof is just to work by induction. So if you start from lambda naught in the bifurcation locus, you perturb it the first time to get a lambda 1 with a Misiurewicz relation. So then you have a family M1 that goes through lambda 1, where this Misiurewicz relation is preserved. And then in M1, you find as close to lambda 1 as you want. You find lambda 2 with a second Misiurewicz relation, lambda 2. And then proposition 1 tells you that lambda 2 must be in Bif2. But since lambda 2 is very close to lambda naught is also in Bif2. And of course, if you have more dimension, the proof is the same. It's just an induction. But now, of course, the question is, how do you prove proposition 2? Because all the work is in the proof of proposition 2. So let me give more information on this proposition. So the conditions that we will require for the persistent Misiurewicz condition, persistent Misiurewicz relation from proposition 2 is we're going to want to say that there's going to be more expansion in the vertical direction than in the other direction. So because we have a skew product, if you take any cycle, any repelling cycle, let's say, you have always one invariant direction that is the vertical direction, right? Because vertical lines are mapped to vertical lines. So you have an eigenvalue that is associated to this vertical direction, and then you have another eigenvalue, and we're asking that the vertical eigenvalue is strictly larger than the other one. Both are more than 1 in modulus because it's a repelling cycle, but the vertical one should be more repelling than the other one. So that's the first condition. And the second condition is that this vertical eigenvalue should be non-constant on the family. And this will be in practice difficult to ensure because, of course, in the induction, the family is going to be smaller and smaller. And so it could very well happen that at some point in the induction, if you're not careful, the eigenvalue becomes constant. And a third property that we need for the argument is that the nth iterate of the critical locus that passes through the repelling cycle because of the Misiurewicz relation, that should not be tangent to any eigenspace of the cycle. And in fact, there are other technical assumptions, but I will not mention them. So let me sketch this condition and the idea of the proof of proposition 2. So we have this picture in local coordinates. So I'm going to draw this picture in linearizing coordinates, and this at the origin is the repelling cycle, which I'm going to assume is in fact just a fixed point, which we can assume this up to passing to an iterate, of course. And then we know that this fixed point, repelling fixed point, is in there's a critical point that lands through this fixed point. So the certain iterate of the critical locus, let me use a different color actually. So there's a certain iterate of the critical locus that passes through this fixed point. And it should be non-tangent either to the vertical direction or to the other direction. And the other condition that we have is that both invariant directions are repelling, but the vertical direction should be much more repelling. Okay, so now we have this picture, and we want to construct by hand a new Misiurewicz relation. So how do we do this? Well, first we take a sequence of repelling cycle that are going to accumulate some point over here. So in red, those are new repelling cycles. And then, using the fact that the vertical direction is more repelling than the other one, when you iterate this Fn of the critical locus, this will tend to get closer to the vertical. And if you keep on doing this, this will get very, very close to the vertical. And as you can maybe sort of see from the picture, you can ensure that some iterates at the critical locus are going to get very close to some of those repelling cycles in red, and then up to adjusting this by a small perturbation in parameter, you can make sure that it lands exactly. You can make sure that this iterate at the critical locus in the green covers exactly 1 point in red. I mean, both of these things, of course, move with respect to the parameter, but you can ensure this. Now there is another difficulty, of course, from this picture. It's that you need to ensure that this new critical relation that you construct over here will again be good in the sense of proposition 1. So you should ensure that you don't have any tangency for this new Misiurewicz relation. So let me try to give a very quick idea of how to prevent tangency in the induction. So this is where we will use this assumption on the base polynomial P. So the idea will be that if you look at this picture, so the direction of the iterate of the critical set should not coincide with any eigenspace of the repelling cycle in red, but the direction of the iterate of the critical locus is very close to the vertical. So what we want is we want to have repelling cycles whose invariant direction are bounded away from the vertical direction. So to do this, we want to, in fact, construct a hyperbolic set and only pick repelling cycles from that hyperbolic set. So it should be a hyperbolic set in situ, right? A hyperbolic set for the map F, for the skew palette. So here we use a recent theorem by Schrettike and Stunik, that say that under the assumption that I've stated on P, the hyperbolic dimension of P is larger than 1, which is basically all that we need. We can replace our assumption with the fact that the hyperbolic dimension of P is more than 1. So you can find the hyperbolic set in the base polynomial with larger than 1 Astorg dimension, and I will have to finish quickly. So from there, you can find a measure on this hyperbolic set downstairs on P that has Lyapunov exponent less than log D. So it averages its average expansion in the horizontal direction is less than log D. But then by some other argument, the average vertical expansion is always at least log D. And then you can construct a measure, a fiber measure on C2, where the average horizontal expansion is less than the average vertical expansion. And from there, let me just in 2 seconds draw a sketch of this, and then you can construct your hyperbolic set by taking a ball in C2, so this is in C2, and then you find nice inverse branches that that map the ball compactly inside itself. And of course, you look at the limit set, and that's going to be a hyperbolic set, and you choose those inverse branches so that the expansion, the vertical expansion, is actually really stronger than the horizontal expansion. And this is what allows you to prevent tangencies. And I think my time is over, so I will stop here, and thank you.